start with the basics. A programmable logic controller, or PLC, is a computer-type device used to control equipment in industrial facilities. PLCs are found everywhere, from conveyor systems to food processing machinery and auto assembly lines. They're designed to automate processes, making operations smoother and more efficient. Unlike traditional control systems that rely on hardwired connections, PLCs use software to manage tasks, offering flexibility and reliability. Whether you're running a single machine or an entire production line, PLCs are the backbone of modern industrial automation. PLCs are everywhere in industry. They control conveyor belts, manage food processing machinery, and oversee auto assembly lines. Their versatility means they can handle a wide range of tasks, from simple operations to complex production systems. By automating processes, PLCs help industries achieve greater productivity and consistency. They're built to withstand harsh environments, making them ideal for factories and plants. With PLCs, industries can quickly adapt to changing demands, ensuring smooth operations and minimal downtime. PLC is essentially an industrial computer used to control a specific process, machine system, or sometimes an entire production line. It's programmed to respond to input signals and execute tasks based on those inputs. This makes PLCs highly adaptable, allowing them to be used in various applications. Whether it's monitoring sensors or controlling actuators, PLCs are designed to handle the demands of industrial automation. Their robust design ensures reliable performance, even in challenging conditions. Let's break down the basic parts of a PLC. The block diagram typically includes the CPU, central processing unit, programming device, input and output modules, and a power supply module. Each component plays a crucial role in the PLC's operation. The CPU acts as the brain, processing data and executing programs. The programming device is used to create and modify the PLC's instructions. Input and output modules connect the PLC to sensors and actuators, while the power supply ensures everything runs smoothly. CPU module is the heart of the PLC. It contains the central processing unit and memory. The CPU reads input data from sensors, executes the user program stored in memory, and sends output commands to control devices. This continuous cycle ensures that the PLC responds quickly and accurately to changes in the system. The CPU's reliability and speed are critical for maintaining efficient operations in industrial environments. Programming devices are essential for configuring PLCs. Typically, a normal computer with PLC software installed serves as the programming device. Sometimes, handheld programming devices are used for convenience on the factory floor. These devices allow engineers to create, edit, and troubleshoot PLC programs. With the right software, programming becomes intuitive, enabling quick changes and updates to the system logic. Input-output modules connect the PLC to the real world. Input modules receive signals from sensors, switches, or other devices, while output modules send commands to actuators like motors or LEDs. These modules are crucial for monitoring and controlling processes. Manufacturers offer a wide variety of I/O module types, ensuring compatibility with different sensors and actuators. The flexibility of I/O module allows PLCs to adapt to various industrial applications. The power supply module provides the necessary power for the PLC's CPU and other components. It also powers sensors and low-power actuators connected to the I/O modules. Reliable power is essential for consistent operation, especially in industrial environments where interruptions can lead to downtime. The power supply ensures that all parts of the PLC function smoothly, maintaining system stability. Input-output processing is at the core of PLC operation. Input devices supply signals to the PLC, indicating events or conditions in the system. Output devices await commands from the PLC to perform actions like turning on lights or motors. The PLC continuously receives input signals, runs the programmed logic, and sends output signals to control devices. This cycle repeats until the system is switched off, ensuring real-time control and automation. The PLC operates by scanning its program in a continuous cycle. This scan cycle consists of three main steps: checking input status, executing the program, and updating output status. First, the PLC checks each input to determine its state. Next, it executes the program instructions sequentially. Finally, it updates the outputs based on the input states and program results. After completing these steps, the PLC repeats the cycle, ensuring timely responses to changes in the system. The first step in the PLC scan cycle is to check the status of all inputs. The PLC examines each input device to determine if it is on or off, recording this information in its memory. This data is crucial for the next step, as it forms the basis for executing the program logic. By accurately capturing input states, the PLC ensures that it responds appropriately to real-world events. Next, the PLC executes the user program one instruction at a time. The program, often written in ladder logic, is processed sequentially from top to bottom and left to right. The PLC stores the results of each instruction for use in the final step. This methodical execution ensures that the PLC follows the intended logic, making decisions based on the current input states. The final step in the scan cycle is updating the output status. The PLC uses the input states and program results to determine which outputs should be activated. It sends signals to output devices, such as motors or lights, to perform the required actions. This step ensures that the system operates as intended, responding to changes in real time. After updating the outputs, the PLC returns to the first step and repeats the scan cycle. This continuous loop allows the PLC to monitor inputs, execute logic, and control outputs in real time. The rapid repetition of the scan cycle ensures that the system remains responsive and efficient, adapting quickly to any changes in the environment. For PLCs, automation in industry relied on hardwired connections. Physical wiring connected devices like timers, counters, and logic gates to achieve automation. This method had several drawbacks, including complexity, inflexibility, and difficulty in making changes. Large wiring panels and masses of electromechanical relays were common, making maintenance and troubleshooting challenging. Hardwired automation systems were inflexible and costly. Any change in system logic required rewiring, which was time-consuming and expensive. Troubleshooting errors meant tracing wires and connections, often leading to lengthy downtime. The limitations of hardwired systems prompted the industry to seek better solutions, paving the way for PLCs. With the invention of PLCs, hardwiring was largely eliminated. Input and output devices are simply connected to the PLC, and the system's behavior is determined by the program. Changing the program alters the system's operation without touching the hardware. This flexibility revolutionized industrial automation, making it easier to adapt and maintain systems. Traditional automation panels were filled with electromechanical relays, all hardwired together. Electricians installed wires based on blueprints designed by engineers. Making changes required physical rewiring, which was labor-intensive and prone to errors. These panels were large, costly, and difficult to modify, highlighting the need for more efficient solutions. The disadvantages of hardwired control panels led to the adoption of PLCs. Industries needed more flexibility, rapid changeover, and reduced downtime. PLCs replaced costly, inflexible panels with programmable logic, allowing quick changes and improved productivity. The ability to update system logic through software made PLCs a game-changer for industrial automation. PLCs offer several advantages over traditional systems. They can withstand severe conditions like dust and humidity, eliminate much of the hard wiring, and contain pre-programmed functions such as logic, timing, and counting. Error correction and troubleshooting are quick and cost-effective. PLCs are space-efficient, low-cost, and allow visual observation of operations, making them ideal for modern industry. Despite their advantages, PLCs have some limitations. Most PLCs use closed architectures, meaning parts and software from different manufacturers can't be easily combined. This limits design and cost options. PLCs are proprietary devices, which can restrict flexibility in system integration compared to open architecture microcontroller systems. PLCs are typically used in industrial environments, while microcontrollers are suited for embedded applications. PLCs are programmed with ready-made blocks or elements, making programming easier. Microcontrollers require coding and programming languages. PLCs are robust and designed for harsh conditions, whereas microcontrollers are smaller and used in specialized devices. While PLCs and PCs share similar architectures, PLCs are built for industrial environments with wide temperature and humidity ranges. PLCs are unaffected by electrical noise and are programmed in relay ladder logic or other easy-to-learn languages. PCs are complex and can execute multiple programs simultaneously, but PLCs focus on running a single program in an orderly, sequential manner. PLCs come in various sizes, from micro to very large. Micro PLCs control up to 32 input and output devices, while small PLCs handle 32 to 128 I/O. Medium PLCs manage 64 to 1024 I/O. Large PLCs cover 512 to 4096 I/O, and very large PLCs can control up to 8192 I/O. The size of the PLC is chosen based on the complexity and scale of the application. Choosing the right PLC involves several criteria. Determine if the system is new or existing, consider environmental factors like temperature and dust, and decide on the type of CPU needed. Assess where the I/O will be located, communication requirements, and programming needs. These factors ensure that the PLC fits the application and delivers reliable performance. A personal computer is the most common programming device for PLCs. The software allows users to create, edit, document, store, and troubleshoot programs. PCs communicate with PLCs via serial or parallel data links. Handheld programming devices are also used for small PLCs, offering compact and easy-to-use solutions for troubleshooting and program transfer. PLCs are programmed using ladder logic, which is made up of contacts, coils, and other functions arranged as rungs on a ladder. The purpose is to determine when a load should be turned on or off. Contacts can be open or closed, controlling the flow of current to the output coil. Ladder diagrams visually represent the control logic, making programming intuitive. A basic ladder diagram consists of a power line on the left, a switch contact, and a load, such as a lamp. The right vertical line provides a return path for current. Horizontal rungs represent individual control circuits. Multiple rungs and contacts can be added to create complex programs, enabling advanced control functions. Ladder logic uses symbolic representations for electrical circuits. The main symbols are normally open, no contacts, normally closed, NC contacts, and output coils. No contacts pass power when closed, NC contacts pass power when open, and output coils are energized when a path exists. These symbols make ladder diagrams easy to read and understand. PLC timers control devices for specific durations. Timer instructions provide logic to decide when to turn circuits on or off. Timers have coils, contacts, and registers. When the coil is on and the set time is reached, the contact is enabled. Timers are used for operations requiring precise timing, such as delays or scheduled action. There are two main types of timers in PLCs: on-delay timer TON and off-delay timer TOF. On-delay timers start timing when activated, while off-delay timers begin timing when deactivated. Delta PLCs support up to 128 timers, allowing complex timing operations in industrial processes. Counters in PLCs track the number of times an input is switched from off to on. Before using a counter, a preset value is set. Each time the input changes, the counter increments by 1. When the preset value is reached, the counter contact is enabled, triggering an output. Counters are used for counting events, pulses, or cycles in automation. Or logic in ladder diagrams is achieved by placing two contacts in parallel. The output coil is energized if either contact is closed, providing at least one path for current. This logic is used when multiple conditions can trigger an action, offering flexibility in control systems. And logic is achieved by placing two contacts in series. The output coil is energized only if both contacts are closed, ensuring that all conditions must be met for the action to occur. This logic is used for safety and precision in control systems, requiring multiple criteria to be satisfied. Not logic inverts the input, typically using a normally closed contact. The output coil is energized when the contact is not actuated and de-energized when it is actuated. This logic is useful for creating conditions where actions occur only when certain inputs are inactive. NAND logic is created by inverting each input in an OR function using normally closed contacts. The output coil is energized if either contact is off and de-energized only if both contacts are on. This logic is used for scenarios where actions should occur unless all conditions are met. NOR logic is achieved by inverting each input in an AND function. The output coil is energized if both contacts are off and de-energized if any contact is on. This logic is useful for ensuring that actions occur only when all conditions are inactive. Latching circuits are used to hold an output energized even when the input is stopped. For example, a motor can be started with a push button and continues running until a stop button is pressed. The latch circuit maintains the motor's state, ensuring continuous operation. Ladder diagrams illustrate how latching works, providing reliable control for motors and other devices. The latching operation involves energizing the motor coil when the start button is pressed. The motor continues running even after the button is released, thanks to the latch circuit. Pressing the stop button de-energizes the motor coil and stops the operation. This stage-wise diagram shows how latching maintains the motor's state until a new input is received. Internal relays in PLCs are elements used to hold data bits and behave like relays. They can be switched on or off and control other devices. Internal relays exist only in memory, not as physical devices, but they function like real-world relays. They are useful for complex logic and can be combined with external inputs to activate outputs. Interlocks make the state of two mechanisms mutually dependent. They prevent incompatible events from occurring simultaneously. Interlocks are used to start auxiliary equipment, prevent system startup for smooth operations, or set stopping conditions. For example, a pump can start only if a valve is open, or two motors are interlocked so only one can run at a time. In the ladder diagram, two motors are interlocked. Motor 1 can start only if motor 2 is off, and vice versa. This ensures that both motors cannot run simultaneously, preventing conflicts and ensuring safe operation. Interlocks are essential for coordinating equipment and maintaining system integrity. Water level control uses PLC logic to manage a tank's filling process. Sensors detect water levels, and a solenoid valve opens or closes based on sensor signals. The start button initiates the system, and the stop button halts it. When water drops below a certain level, the valve opens to refill the tank. When the tank is full, the valve closes. This automated cycle ensures efficient water management. The ladder diagram shows how the PLC manages water levels. When the start button is pressed, the system begins monitoring sensors. If the water drops below the sensor, the valve opens to refill the tank. As water rises, the valve remains open until the upper sensor is triggered, then it closes. This logic ensures the tank is always filled to the desired level. Pressing the stop button deactivates the entire water control system. The PLC logic ensures that all operations cease and the tank stops filling. This feature allows for safe and controlled shutdowns, preventing overfilling or unnecessary operation. The PLC's ability to manage start and stop conditions is vital for efficient and safe automation.